Welcome everybody. It's almost my bedtime here in Nova Scotia. It's running for 8:30. So I have a presentation here for you this evening on the PHIUS Institute of the German standard versus the PHIUS climate adjusted standard and how they compare. We started off designing and building passive houses. I think I was in the class one after Adam, so about 8 years ago. And of course, the one standard fits all was running with PHIUS at that point in time. And so we've certified 5 projects to the PHIUS standard, and we're now up to 8 certifications in total. And so 3 of those have been certified with the climate adjusted standard, and we have 3 more in the pipeline. So we've had quite a bit of experience in the last year or so on the difference between these 2 standards, so I thought it might be helpful to share some of that information with everybody. So for most people, let me just get there we go. There's a screen over my PowerPoint. So everybody, I'm sure, is very familiar with the PHI standard of 15 kilowatts per meter squared, heating and cooling, and a 10 watt per meter squared peak heat load. And I put those numbers 4.75 and 3.1 in brackets because the climate adjusted standard is in imperial, so just to give you the comparison. The total energy consumed in the PHI standard is 120 kilowatts per meter squared with a primary energy factor of 2.7. And air tightness was measured in air changes per hour with a limit at 0.6. So we're all pretty familiar with those numbers. Okay, so let me just see if okay. Just takes a second for to advance here. So, okay. So some of the challenges that we were really seeing with the annual heat demand target, the climate zones, as I've shown just here in Canada, range drastically. And then when you add the deep south and their humidity and cooling loads, we have a really wide range of climate zones in North America, much wider range than we have in Europe. In many regions of Canada, we have longer winters and more heating degree days and more solar radiation than Central Europe does. The one exception to that is likely around Vancouver, where looking at the climate data in that area, the solar radiation and the heating degree days is quite similar to Central Europe. The annual heat demand does not ensure comfort, and with the PHI standard, you could achieve either the peak heat load or the annual heat demand to reach certification. In many areas of Canada, and I know in Upper Canada, as we call it, there is a significant cooling load, but here in Nova Scotia there's a very tiny cooling load. Most people don't have air conditioning in this region. So, and then the German standard was based on the German TFA, which is treated floor area, which was a definition defined by the rental, how to define a rental market. So, or the space provided in a rental market. So somewhat different than the way how we normally account for conditioned space in North America. So our response to that annual heat demand of 15 kilowatt hours per meter squared, we've tended as designers to really rely heavily on solar gains to reach that target. And what they're really noticing at PHIUS over the last 5-8 years since projects have been being built and monitored is this large amount of glazing on the south side is leading to overheating in those shoulder seasons. And we are also finding we're having to use some strategies that were not always cost effective. For example, putting a preheat loop on an HRV for the cost of about $2,500 and having about a 65-year payback. The other design response was to reduce the north glazing, which has often impacted the building aesthetic, as you can sort of see in this affordable housing project in Urbana. There's some challenges to the primary energy target as well. The North American grid is just not as efficient as Europe. Our plug loads are proving, plug and appliance and lighting are just proving to be much higher. So it hasn't been very accurate in the energy modeling, and we're really relying on waste heat from these internal heat gains to make the annual heat demand targets when we're monitoring. And then the normalizing the area or having a metric of primary energy target that's based on a per square foot or meter really penalizes small buildings and doesn't encourage density. So big buildings with lower density are reaching certification much more easily, which in principle is just not fundamentally as green. So to give you an example of this, we had two projects built at about the same time. One was about an 8,000 square foot office building, and one was about a 1,200 square foot house. And the 1,200 square foot house had a final ACH of 0.66, and it was one of our early projects, and we thought by putting in drywall we'd squeeze out that last little bit with a bit of air tightness strategy and drywall, but we did not reach that target. The builder was celebrating really strongly with his 0.37 air changes per hour in the commercial building. But when you compare those two on the air tightness per foot squared of building envelope, the small house was actually more airtight than the big building. So again, penalizing those small buildings. So as we were just talking about, the air change per hour is based on the volume of the building. The calculation of that volume is not an ASHRAE familiar calculation, and so it's focusing on that air tightness rather than the building science, with those large buildings being able to have some pretty severe leaks and still achieve their 0.06 air changes per hour. So PHIUS partnered with Building Science Corp and received a bunch of funding from the Department of Energy to develop the climate-adjusted standard for passive house. The first objective was really to make sure that the building envelope was set at a level that made achieving the path to net zero achievable. So there is a trade-off point where stopping the investment in the building envelope and investing in renewable technology makes better, has a better payback than continuing with the building envelope. The second objective was to have simplified formulas that could be used in the design and verification, that they could continue to update for a particular location based on the energy cost parameters and the specific climate. So these targets will change, and actually there's another version of the targets coming out. I'm not sure if they're all published yet, but if they're not, they're coming soon. So the way that they did this is they used a software tool called VOP, and if you can see my arrow on the screen here, what they're trying to do is really hit that point on the curve where this is the energy use and cost. So where the energy use dropped and the cost start up, just what they called the kind of the hook of the hockey stick was kind of the most cost-effective point, and they did this for each of the climates specific shown on the map on their website. So in Nova Scotia, the annual heat demand is now 6.9, and the peak heat load is 4.5, and those you have to hit both of those targets for certification in the PHIUS climate adjusted standard. The total energy consumption is less than 6,200 kilowatts per person, and they increased the PE factor, basically evaluating the grid and saying that the North American grid is less effective at delivering to site, so that we have a higher PE factor, which gives us less site energy to work with our targets. They added the calculation of plug loads at 80% of ResNet calculations, which is much higher than the German estimates for lighting within a passive house. The air tightness metric was changed to a CFM per square foot rather than a air change per hour based on the volume. So the climate adjusted standard on the thermal performance, the heating and cooling targets are adjusted by the heating degree days, but also other climate factors like solar access and solar radiation. The total heating and cooling degree, heating and cooling annual demands targets are less than the PHI standard for Halifax. I'm not sure exactly how they fare out in other places, but we have like 1 kilowatt for cooling and about 20 for heating. So we have a total of 21, whereas the European standard would allow 30 total for those two things in combination. The area is calculated using ICFA. This is more standard than the German TFA. It's an ASHRAE defined international conditioned floor area. In some designs it makes it, you get more square footage to work with for your energy budget because it counts stairways and it counts all spaces, I believe, above 6 feet. But anything under 6 feet, which you did have some allowance for in the PHI calculation, those are lost in the ICFA calculation of the climate adjusted standard. These targets are cost optimized using the software BOP, and the targets are really set to minimize the mechanicals but still ensure comfort, and that's the logic behind having both the peak heat load and the annual heat demand as requirements. But the peak heat load is much higher than the allowable defined by the German standard to distribute what's safe to distribute as heat through the HRV ducts. I think in most projects, a separate heating system in the Canadian climates are required. We have had very few projects that we've had the heat demand be low enough that we could deliver it through the HRV. So again, the ICFA is typically a little bit higher, so because the annual heat demand is a metric based on square footage, your budget is a little bit higher there. But these numbers are currently and constantly being fine-tuned by PHIUS as part of the standard. On primary energy, the higher plug loads means you have more internal gains, but also a higher baseline total energy. So when you think about it, if you have the higher plug loads plus you're allowed to use more energy for the annual heat demand, it starts to really and we have a less efficient grid, so we have a higher PE factor. It makes that primary energy number more difficult to hit than the PHI standard in our experience. The fact that it's normalized by number of people and not area, I think, is a much more equitable way to decide the site energy that's budgeted in a project, and it's based on occupancy on number of bedrooms plus 1. So if you're doing a multifamily unit, let's say you have a quadruplex with 4 2-bedroom apartments, then your occupancy is 12. So number of bedrooms plus 1 for each unit. This really encourages small houses with more density, which I think everybody would agree is a better green principle going forward overall. And we're noticing that the domestic hot water is as important to the PE as the annual heat demand, because we're typically using a ductless mini split. That domestic hot water component of the energy budget, as I call it, is something you really have to keep a watch on. And in the new standard, in both standards now, there's an allowance to count PV to offset the primary energy target. And I haven't done a certification to the German standard since they've added this component. But with PHIUS, it is calculated on what you can use on site. So you can put on more PV than they'll allow you to count. But so far we haven't had a problem with not being able to count the PV that we've put on that we need for reaching our primary energy targets. And in almost all our projects, we're finding that a heat pump, solar thermal, and/or photovoltaics are required to achieve the primary energy target. So as I said, with those higher plug load calculations and a higher annual heat demand, although we have a lower cooling load, we weren't ever using that anyway. So the primary energy target is quite stringent and difficult, as it should be to reach. On the air tightness, I find that the air tightness across the building scale is a better way to measure. Again, not penalizing those small buildings, and it also reflects the building science requirement of air tightness a little bit better, making sure that you don't have basically a leaky envelope in a big volume building and therefore having too much air moving into your walls. So the big challenges we've seen is the higher, as I talked about, the higher annual heat demand is leaving less energy budget for the rest of the energy use in the house. Much harder to hit the PV in larger homes with fewer bedrooms. We've always needed a heat pump or solar thermal hot water and a heat pump for heating if the house is all electric. The air tightness metric is a little harder to understand. Because people can wrap their head around air changes per hour, but CFM per square foot building envelope is more difficult to kind of get your hands around. The peak heat load has actually been the hardest for us to hit, and I'll say from our experience that I'm still really questioning those targets set by PHIUS, and we've been energy modeling a large number of projects and preparing a document to send into the PHIUS Tech Committee that kind of makes an argument that in our climate, and we've modeled them in 7 climates in Canada, the annual heat demand is usually having to go back down below 4.75 in order for us to hit the peak load. And the peak load is really there to maintain comfort. So we're really back to the PHI target for the annual heat demand, which means more strategies that maybe not cost effective in the building. So we're making an argument with PHIUS that the peak heat load targets may be set too high to be cost effective. So, and one of the strategies that we're using to help reach the peak heat load is we're still targeting 0.5 air changes per hour on most of our projects. We've been achieving kind of from 0.4 to 0.5 very regularly on projects, so we're confident in doing the energy model at that level. Whereas in the square foot, the CFM per square foot metric, on a smaller house you can have an air change up to about 1 and still meet the PHIUS challenge, the PHIUS target there. But we can't reach the peak heat load target, so we're still targeting quite a low air change per hour. We find that the targets are a bit more confusing to the industry because there's just so many more numbers out there. And one of the other challenges is that the mixed commercial and residential, because the mixed commercial is still operating on a primary energy metric of kilowatts per meter squared, and the residential is that 6,200 watts per person. We have to model mixed use buildings as basically as two separate projects. So I wanted to just talk a little bit about the Alice Street pilot project that we did as a bit of a case study, and this is where we got really interested in looking at the PHIUS climate adjusted standard. So this was a housing Nova Scotia, affordable housing project in a small town in Nova Scotia. It was really defined by its building scale and topography. It was a 3-bedroom duplex, and the schematics and elevations were already completed when we joined the team, and the proposed plan was very close to the maximum buildable area of the lot, and the lot had extremely poor solar access. So this is the streetscape. This is the house that was torn down. It was only about 30 years old, but it was all moldy, and a perfect example of why not to build the old way. And one of the things to really notice was, you know, we had really good orientation on the lot. We had a relatively south-facing backyard, so we should have been in relatively good shape for the energy model. But all of these giant trees at the back of the house are on a school property. So as you can see from this Pathfinder, there's just a massive amount of shading on this property. The initial design was really responded to the street context and the building vernacular, and it was actually quite good as a compact building design. These little dormers are just false roof vents, so it's just a duplex, and it's a cube. So it should have performed quite well. There was a symmetrical plan on the duplex, a fairly centralized plumbing, and a 3-bedroom unit in each side of the duplex. So we applied the passive host principles of thickening the walls, centralizing the plumbing, prioritizing the south windows, and maximizing the ICFA. And the thick walls required a redesign, and we filled the remaining space on the allowable footprint of the lot based on the setbacks. We tried to specify tested and locally available materials in the assemblies because this was a project that would be tendered to a local builder, and lowest price was awarded the contract. We did shift around some rooms and walls to get more usable space. But what the energy model showed us was that all those south windows were just a negative, actually, in the energy model. So the passive solar principles were just not helping us reach the annual heat demand target. So we enlarged the footprint to the maximum setbacks on the project. Because we made the walls thicker, we had to make the building a little bit deeper to maintain the same living space inside. And we made a few changes to the plan to maximize the conditioned floor area. So the energy model clearly showed us that achieving the PHI standard would not be cost effective. We were constrained on the building thicknesses, the wall thicknesses, and the building shape and orientation was already optimized, but that shading that we had no control over in the backyard really made it very difficult to achieve. So here's some of the numbers. So we started with basically what Housing Nova Scotia would typically build, and we were at 21.21 BTUs per foot squared per year, and that remembering that the our PHI standard would be 4.75. So you can see we applied the passive host assemblies. We brought our air tightness down to 0.6. We put in triple glazing, double coated, low E argon filled windows, fiberglass windows, the best Canadian HRV that we could buy. Then we looked at the ground loop, some redesigning of the spaces and increasing some of the windows, reducing the north windows, moving the third bedroom to the south and having to excavate out the backyard because of the slope. We're still not there. So the only thing that we could practically do was try to cut down 30% of the trees in the backyard to get us to the 4.75. And so Mike, Anderson, who works with me and does a lot of the energy modeling, made this little table for us that shows, we kind of got, if you could see my mouse, we kind of got down to this level, which was around the 7. And then all those incremental changes of just trying crazy things like 40 inches of insulation in the roof made almost no difference, 100 inches of insulation, no difference, 20 inches in under the slab, 40 inches under the slab, best airtight ever. I'm not sure what Mike used for that. And then thickening the walls, having about an 18-inch thick wall, and then going up to a 23-inch wall. And basically, to get to that 4.75, we had to do all of those things to get us down to make the standard. So we couldn't do this without passive solar. So then when we worked as a pilot to the climate adjusted standard, the improved solar was not required. The small high occupancy of the building meant we were in better shape for the primary energy targets and the air tightness because the building was quite a compact building shape, so we didn't have a huge surface area of building envelope. There's no natural gas available at the site, so this is an all-electric site, again pushing the primary energy target. So we needed to upgrade some mechanical system in order to achieve even the climate adjusted standard. So here were the cost-effective strategies that we put in to hit the annual heat demand. Really, this was done by using design and assemblies without having to go into any other level. So there's the graph that shows how we got under the climate adjusted standard. So then we looked at the mechanical choices. Simple mechanicals that they would typically use were not enough to hit the primary energy target. We looked at a ductless mini split instead of electric baseboards, but because this is a rental unit, they didn't want the maintenance or the expense related to the capital cost or the maintenance cost, even though the maintenance is quite low because they have 11,000 units in the province. It's just another thing that they have to try to take care of. Upgrading to a German-made HRV was not permitted because it was a public housing project. It had to be a Canadian-made product for the HRV. The idea of photovoltaics wasn't very good because we had poor solar access to the south, and the panels are still pretty expensive for their return on investment. And solar thermal hot water, the same poor solar and higher maintenance for the staff. So the solution that we went with on the mechanicals was a hot water heat pump, and this building just has electric baseboard heat with a standard thermometer that anybody knows how to get the heat running, and almost no maintenance. So our conclusions were that the design should be based on a cost-effective optimization and energy modeling, and that this compact 3-story duplex with a good design should be able to reach the passive house standard without having very good solar access. and we were able to, we've been able to show that it's very achievable and cost effective in Halifax. It's somewhat untested by us in other climates. I'm sure others out there are starting to design an energy model to these numbers. And we're really interested in where's that cost balance between how you invest in the building envelope and where do you then turn to renewables, especially with the cost of PV coming down over time. So that's all. That's the end of the presentation. And I think we have maybe a couple minutes. If folks have any questions, you can type them into the chat, and Stefan could read them out so we can all hear them.
There is one question from Patrick, and he asks, what was the final cost versus a code-built version?
Yeah, that's a great question. They're doing some analysis on what their final costs were, but interestingly enough, they had a construction budget for this project before they decided to go passive house, and the RFP response that was contracted was under that budget amount. So for them, they were able to upgrade to passive house without a lot of additional costs. I think the contractor that got the contract made some investments in the learning process. I've had several conversations with him, and he said, you know, he would be a lot more efficient next time, but he still did okay on the project. Obviously, if they built the exact same house as a co-built house, it would have been less. But having been really aware in the design to make sure everything was buildable and simple, and using locally available materials and things that the guys are used to working with, but putting them together in different ways, I think really helped on the cost effectiveness. The contract was awarded at $127 a square foot, which is extremely low, even in our market.
All right, great.
Excellent.
The next question was from Greg Leskine, and he asks, can you comment on the use of the best Canadian-made HRV you referred to in your project example in terms of how you entered the performance characteristics into the PHPP and WFI passive? Is there a lot of
Yeah, sure. There's actually a resource on the PHIUS website. Somewhere in there's like tools and resources, and there's a spreadsheet that PHIUS put together, which has been extremely valuable in making the energy modeling discipline, but also in evaluating which units to look at. So what they did was a lot of Canadian HRVs going to dump the waste heat from inefficient fans into the supply air, thus bumping up the sensible recovery efficiency numbers, but the electrical use is really high. So what PHIUS did is they kind of separated that out and made an adjusted sensible recovery, and also collected the watts per CFM or CFM per watts. Can't remember which order the units go in, which are the two numbers you need for energy modeling in both PHPP and WFI passive. So that sheet's available. It's publicly published on PHIUS's website under their resources.
Great. And Peter Schroner asks, was the heat pump domestic hot water drawing heat from the indoor air adding to the heat load an issue?
Yeah, another good question. So there's a mini calculator, and I believe this is in the resources page on PHIUS as well, that basically says that you know, for a certain time of the year, you're definitely drawing heat out of the building and cooling the building that you're having to replace with electric baseboard heat. So there's a calculator that downgrades the overall COP of the heat pump for the hot water based on what your climate data is, but also what your heating system is. So there's a little calculator to adjust that. This building has been occupied since April. So this is the first winter, and they have monitoring data in the building, but I don't have any of that data yet. But the hot water heat pump was placed in the basement next to with extra venting into the storage. So I don't expect it'll be affecting comfort based on some of our other decisions, but it's definitely discounted in the energy performance in PHPP with that calculator.
Great. Patrick asks, do you have any projects that are being monitored for energy use? If so, how are the monitored projects comparing to the actual usage?
Yeah, so this project has kind of great because it's 2 occupants, neither of which are passive house enthusiasts. They're just affordable housing tenants. But I don't have any of that monitoring data reported yet. As I said, the clients just moved in April. We monitored the Hawkins passive house for about 2 years, and it definitely showed that some of the heat, like the heat load, was quite low in the house, and the electrical usage was higher than this house was certified to the PHI standard. It followed that trend that PHIUS reported that there was higher internal heat gains from plug loads and lights and appliances that were assisting the overall use in the annual heat demand, but the overall use in the building was very close to target, just a tiny bit over those first 2 years. There's a 4th project that's being monitored in Nova Scotia as well, but it's not occupied full-time, so the data is a little less relevant.
Okay. And William Murray asks, what type of windows were used, and did they get included in the $127 a square foot cost?
Yes, they did. The window package on this project came from Accurate Doorwin in Winnipeg, and they tendered the windows to 3 fiberglass manufacturers, and Accurate was the one that got the contract. That Housing did another 9-unit building that we're in the process of certification. Clients just moved in there about 2 weeks ago, and they also use the Accurate fiberglass windows. We've started modeling a vinyl window manufactured in Nova Scotia, and surprisingly their performance data is extremely close on some of their products to the fiberglass, and they're about half the cost. But the fiberglass was part of the $127 a square foot.
And I've got a question. The PE value, was that achieved on on that project?
Yes, it was, Stephen. And the main reason it was the two reasons it was achieved was our annual heat demand was actually down somewhere around, I think, about 5 because we achieved quite a good air tightness. I think the final air tightness was like 0.43 on that project, so that helps quite a bit. Because it's quite high density, so it's 4 occupants in a relatively small building. So our energy budget was quite good. So we just had electric heat and a hot water heat pump, Energy Star appliances, nothing really as special on the appliances, and we reached the PE.
If PHIUS reduces the PE value down to, what is it, 4,800 kilowatt hours per person per year, do you think you would reach it?
No.
That's going to be really challenging.
Yes, that's going to require PV, and it's going to really affect the cost-effectiveness of some of our projects. My personal opinion is that's a mistake at this point in time. I feel like we're just moving into the mainstream, and requiring people to buy solar panels to get a certified passive house, I think will be a barrier to the market, and I think we're just starting to make ground into the mainstream. So my opinion is quite strongly that that's a mistake at this stage.
Natalie, yeah, it's Rob here. One question: Did you use Whoopie Passive on the project? And if so, did you have any trouble getting the climate data for your area, for Nova Scotia?
We use PHPP on this project because it's been going on a long time. So we started the project in PHPP before we do use Whoopie Passive, but we're not using it on every project. On simple projects, we're still using PHPP because we have 3 of us that energy model, and the Whoopie Passive free license is really doesn't have much in the databases, so it's not very useful. And the license is $600 a year for Whoopie Passive. So and it's an annual license, and the multi-year doesn't really save you much. So we're still using PHPP, but on a more complicated or on multifamily or larger buildings, we're definitely using Whoopie Passive.
Okay, thank you.